All right, you guys, asynchronous week 2, we're a quarter of the way done after this. I know it seems like we just started, right? Very exciting times. All right, so we're going to be starting chapter 2 now. Chapter 2 is all about rates of change and the derivative, mostly focusing on the derivative. The derivative is a slope, which I'm going to kind of teach you about as we work our way through here. You're going to get that pretty quickly. We're going to start out doing things a little bit more slowly, kind of relating things back to what we learned about with limits in chapter 1. And then next week, as we move into 2.3, we're really going to focus on kind of doing things a little bit more shorthand with derivative rules. So if you're kind of frustrated by like 2.1 and 2.2, thinking like, you know, I took calc in high school and we didn't do it this way, it was much faster. You're getting the background theory behind whatever we're going to be doing for the rest of the chapter right now. And then next week, we're really going to move into using those derivative rules, which allow you to find your derivatives a little bit more quickly. But first, let's start out with 2.1, rates of change and the derivative. By the way, the title of chapter 2 is the derivative. So this is going to be our main focus, the derivative. Okay, so let me give you an illustration here. Your book probably has a picture that's really similar to this. Let's look at a function, and we're going to be looking at a curved function because that's the whole point of doing this in calculus. Otherwise, we would just be doing linear functions in algebra. Maybe something like this. We have some function y equals f of x. Now, let me pick a good point on this function. We don't want anything too crazy. Maybe something right here. And we'll call this point P. And we'll call this point over here, maybe somewhere like that. We'll call it Q. Now, what we're going to do here is we're going to label P. And we're going to label it as this point C, f of C. Now, of course, f of C is just the corresponding y value. So P is just going to be C, and then the function value at C. Now, the point Q, we're going to let be represented by x, f of x. Now, what we're going to do here, really in the first couple sections, is we're going to talk about what happens as we move our points incrementally closer together. So what we're going to do here is imagine that we're moving this value of x in towards C. Now, if you were to actually look at the rate of change, which is the slope between the points P and Q, let's see if I can connect these with a nice smooth line without making this look awful. I have no straight edge that isn't giant. Let's imagine connecting these with a secant line. And a secant line is just a line that connects two points that run through a curve. Okay. All right, so you've got this secant line. I'm going to label it as such. If I can find a good spot to label it. Now, the slope of the secant line will just be the slope from P to Q. So if we want to go ahead and label, remember we usually use M to denote a slope. So we'll say that the slope of the secant line is the change in y over the change in x. So you did this in algebra. In algebra, we used y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Same idea here, but this time now we're using y sub 2, which is f of x, minus y sub 1, which is f of c, divided by x sub 2 minus x sub 1, so x minus c. And this will give us the slope from P to Q. Now, what I want you to visualize here is that we can take this point Q and we can move it closer and closer and closer to P along this curve. Now, at some point, once Q gets really, really, really close to P, we're going to end up getting these values to approximate a tangent line on this curve. Now, a secant line is a line that runs through 2 points on a curve, but a tangent line is a line that just touches 1 point on the curve and then continues to move on its way wherever it's going. So imagine that I can move x closer and closer and closer to C. If I were to do that along this curve, the point Q would move closer and closer and closer to the point P, and eventually they would come together and they would give me this tangent line that is approximately tangent to this curve. You're going to have to estimate that. I didn't get close enough there. But you would end up getting a line tangent at P. So let me summarize this for you in words. As Q gets closer to P, the closer the secant line gets to becoming a tangent line. So the closer the secant line becomes to a tangent line. Oh, sorry. Okay, so you're moving this point Q over and over and over. As you continue to do so, you're switching the secant line. I mean, imagine if you had a new point, let's say we called it Q sub 1, maybe, right here. Well, your secant line would then go like this through P and Q sub 1. Now we're making this graph a lot messier, so at least you saw it in its original form before we mutilated it. But you would have this other secant line then, and you can see then as you move your way closer and closer to P, well, let's say I moved on this curve and put Q sub 2 right here, you would see then that your secant line starts to get closer and closer and closer to a tangent line. So the tangent line is just the point that hits the curve in one spot and then keeps going, kind of like bounces back off of the curve. Okay, so this is the idea here. Now, if you're having a hard time making the connection between this and what we did in chapter 1, well, what's happening here is when we move this point incrementally closer and closer and closer to point P, what we're doing is we're finding the limit here. This as we move our way through from one point to the next. So what we do when we find a limit is we take one value and we move it incrementally closer to another. And that's what we're doing here with this slope of the secant line, and we move it into a tangent line. And if you're wondering, why would I care about what's happening with this tangent line? Well, sometimes it's helpful to know the slope at some point on a curve, and you might not even know what point you're trying to find the slope at. But what we're going to be doing is we're going to be coming up with formulas for derivatives, which will tell us the slope at any point we would like on a curve. You didn't need to worry about this in algebra, because when you were in algebra, you were only talking about slopes as they related to straight lines. So you just worried about the rise over run, talking about slope in that way, and the slope was always constant. We'll notice that when you're on a curve, the slope is going to be different depending on which point you're at. Like if I'm talking about this point, well, the slope of the tangent line at this point is just this positive line. I don't know, it looks kind of like maybe 1.5 or something. Either way, it's positive. And as we move over here to a point maybe on this part of the curve, the slope of the tangent line would become negative because it's heading down from left to right. So depending on where we sit on the curve, that's going to change the value of the slope of the tangent line. And I don't know, what if we wanted to know what happened at the top of this curve? interestingly enough, our tangent line would look horizontal. So we're going to get back to that idea also a little bit later on here, maybe next week. All right, having said all this, let me define for you the tangent line. We'll talk about tangent lines a little bit more. Definition, tangent line. Tangent line to the graph of f at a point P. The tangent line to the graph of f at a point P is the line containing the point P and remember that we put P at C, f of C, and having slope okay, now here's where your slope definition comes into play here for your tangent line. New notation alert f prime of C. F prime of C. The prime is this little apostrophe looking character, and that's how we would read this, f prime of C. We're going to be using that notation for the rest of our calculus lives. So you're seeing it for the first time now. You're going to be seeing it through the rest of this course, Calc 2, Calc 3. It's not going anywhere. This is going to represent the slope of your tangent line, and we'll represent that by m sub tangent. Remember, m is representing a slope. And then this is going to be equal to the limit as x approaches C, and that's what we did up there in our graph. We were looking at what happened as x approached C. So we're going to do that in our limit. And then we're just taking the slope here, the slope of the secant line, f of x minus f of C divided by x minus C. Now this is provided that the limit exists. Okay, so I know it's kind of odd, but I feel that in some way this should be somewhat intuitive to you because we're taking the slope of the secant line and we're saying by taking this limit, what's happening as x gets really, 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 really close to C. And by taking the limit, we're sending that difference into this really small incremental value. So x is approaching C. As it gets closer and closer and closer and closer, what's happening to the value of the slope? All right, so having given you that definition for the tangent line, we'll give you this theorem about the equation of a tangent line. Equation of a tangent line. Okay, if the slope of the tangent line, f prime of C, exists, so if m sub tan equals f prime of C exists, then an equation of the tangent line, a lot of times I abbreviate equation as EQN just because we end up writing it a lot. It's not because I'm really lazy. I just also feel that you guys don't want to keep rewriting it. And then my writing starts to get more messy. Then the equation of the tangent line, an equation of the tangent line, to the graph of a function y equals f of x, at the point P, CF of C, is, and I'm going to give you the the equation here. Y minus f of c equals f prime of c times x minus c. Now this is going to come back at some point. You might not even see it till you talk about Taylor's series later on in Calc 2. I don't want you to feel that like, oh, holy cow, this is some crazy formula that I have to memorize. I mean, technically, yes, but this is really from algebra. Do you guys remember point slope form? Y minus y sub 1 is m times x minus x sub 1. That's all this is. Point slope form from algebra. So you use this form for an equation to write the equations of lines. Same idea here. You're just, in this case, talking about what's happening at this point, C f of c. Oh, sorry, C f of c. I said that backwards instead of x sub 1, y sub 1. And then the slope we know is represented by f prime of c. So same idea. And then if you still are like, well, where did this come from? Well, think about it. Y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1 is your slope formula. That's where this came from. Multiply both sides of the equation by x sub 2 minus x sub 1, and then just replace y sub 2 and x sub 2 with a general x and y. That's where this comes from. So everything starts out with your slope formula. Then you kind of build it backwards. And in this case, we're just replacing m with f prime of c, and we're replacing c f of c, or I should say we're replacing x sub 1, y sub 1 with c f of c. So either way, this is the equation for your tangent line. We're going to use this now. I'm going to give you one more equation, actually, and then we're going to use this in an example and talk about finding an equation for a tangent line at a point on a graph, which is always very cool. Okay, so that's the equation for your tangent line. Your book really likes to talk about the equation for the normal line. Ugh. I've never seen such emphasis placed on that, but they only really talk about it in this section, and then you don't really use it again. And I would skip over it, except all the WebAssign problems ask you for both equations. Therefore, we must talk about the normal line. The line perpendicular So we remember what perpendicular is, right? Usually you see this symbol for perpendicular. Perpendicular is hitting at that 90-degree angle. The line perpendicular to the tangent line at P is called the normal line. To the graph of f at P. And then that equation is very similar. The difference is that the slope has the perpendicular slope. So you should remember from algebra that slopes that are perpendicular are opposite reciprocals. So the y minus f of c part stays the same. The only difference is we're going to switch out f prime of c with negative 1 over f prime of c. So instead of talking about the slope like we did here, we're going to do the opposite reciprocal of the slope, but everything else will stay the same. We're still going to multiply that by x minus c, just like we did before. So notice for the normal line and the tangent line, everything is the same in these two equations. The only difference is instead of f prime of c, you have negative 1 over f prime of c. Okay. So there's that. Oh, okay. We're not really going to be using the normal line in this class. Honestly, you might not even use it again until Calc 3. I can't even think of an instance where you use it, which is why I don't know why they emphasize it, but that's okay. It's really not that hard to find, so we'll just We'll just do it. Okay. Sorry, you know what? There, that's a little better. Example 1, find the tangent and normal lines to each function at the given point. Find the tangent and normal lines to each function at the given point. Graph all three on the same set of axes. Axes was an answer in the New York Times crossword puzzle on Monday. It was something like the clue was like X and Y on a coordinate grid, and it was 4 letters. And I was like, axes, hello. Anyway, I always like when they put math in the crosswords. Example A. F of x equals 2x cubed minus 1. And we're going to look at this at the point 2, 15. Now, when I give you 2, 15, that is your point C, f of c, just so that we're all clear on that. Okay, now, what we need to do first, I mean, think about what we're looking for here. We need the equation for your tangent line, so we need this guy. We have c, f of c. The only thing we're missing in this case is the slope. So I need, first find f prime of c. If I'm going to find f prime of c, I need to go back to my equation or my definition here for the tangent line. F prime of c is the limit as x approaches c of f of x minus f of c divided by x minus c. So this is what I'm going to find first. I'm going to find this limit. I'm going to rewrite that here for you. So this is the limit. And remember, we're sending x off to c, and we're taking f of x minus f of c divided by x minus c. Okay, so the change in y over the change in x. And we're going to just fill all this in. I have a c. My c is 2 right here. So I'm going to send x off to 2. And I'm going to take my f of x. F of x is 2x cubed minus 1 minus f of c. F of c is just f of 2. F of 2, well, if you want to find f of 2, I already gave it to you, actually. F of c is 15, never mind. Already gave you that. So this is your f of x. And here's your f of c, your y coordinate. And then we're going to divide that by x minus c. In our case, c is 2. And we're going to simplify. So we're going to look at the limit as x approaches 2 of 2x cubed minus 16 divided by x minus 2. And if you want, maybe we should pop this out of the limit for a second just so we can work on it separately, because we're going to have to do a little bit of work here. Not too much, just a little bit. All right, factor out your 2. And if you remember from class the other day, I gave you the formula for the difference of two cubes. That's what you're going to use here. I'm going to remind you of what that formula is. I'm going to even say, recall that a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. This is a formula from algebra. So we have a difference of two cubes up here. 8 is 2 cubed, and then x cubed is clearly x cubed. So we're going to rewrite this as twice. Then we'll have x minus 2, and then x squared plus 2x plus 4. So b in this case is 2, b squared would be 4. And then that whole quantity is getting divided by x minus 2. Cancel out the x minus 2's, and that leaves you with 2 times x squared plus 2x plus 4. So now that you know that, go ahead and put it back in your limit. If you want, you could put the 2 in front of your limit. You don't have to leave it inside. Leave that up to you. But the denominator is now 1, so you don't have to worry about that. So this would be just 2 times 2 squared plus 2 times 2 plus 4, which is 2 times 4 plus 4 plus 4. 4 plus 4 plus 4 is 12, times 2 is 24. Now this is f prime of c, which, by the way, is, I know we labeled it as f prime of c. For us, it's actually f prime of 2. I should have written it that way. That'd be the best way of writing it. Because we're really looking for f prime of c, which I put here. In our case, c is 2. Okay, so this is our slope. So f prime of 2, which is the slope of your tangent line. And really, once you find the slope of your tangent line, the rest of this is not going to be that big of a deal. You're just going to piece it all together using the equation that I gave you. Y minus f of c equals f prime of c times x minus c. I'll leave that right here for you. Y minus f of c, we said was 15, or I gave that to you, is equal to f prime of c, which is 24, times x minus c, which is x minus 2. So this is the equation. You just need to simplify it. You have y equals, I should still keep the 15 there for a sec. Y minus 15 equals 24x minus 48. And then add 15 on both sides, and you get y equals 24x minus 33. And this is the equation for the tangent line at x equals 2. Now, I did write in the directions that when you do this, we're going to graph the tangent line, the normal line, and the graph all on one set of coordinate axes. For now, don't worry about it. Just let it be. We'll graph those in a minute when we get done with the normal line. Okay, so that's your tangent line. Now, for the normal line, you know, we actually probably can put this on the same sheet. Remember that we're just using the slope that is the opposite reciprocal. So for your normal line, you have y minus f of c equals -1 over f prime of c. And if you don't remember where that came from right here. The equation for the normal line, we're going to use this one. And then we're going to multiply that by x minus 2. So same exact thing here. The only difference is we're taking the opposite reciprocal for the slope. And then we have y minus 15 equals -1/24 x plus 2/24 simplifies to 1/12. and I'm going to add 15. So 1/12 plus 15. Oh, by the way, for those of you who are not so savvy with your calculators, when I entered 1/12 plus 15, it gives me a decimal, but if you hit this math button and you hit enter twice, it'll switch that into a fraction for you. And you get 181/12. So we'll have y equals negative 1/24 x minus, oh no, plus 181/12. So this would be the equation for your normal line. And I did ask you to graph them all on the same set of coordinate axes. Now I'm wishing I would have used a different point instead of 215. I actually made a note to self to change the point, and then when I looked at my notes later, I was like, why would I do that? The point's fine at 215. Sometimes I need to make better notes, clearly. Okay, but that's fine. It's all good. Okay. Original graph, original function, I should say. Well, 2x cubed minus 1. 2x cubed minus 1. We're going to have to play around with our window a little bit to see these lines. Tangent line, 24x minus 33. Normal line, negative 1/24 x plus 181/12. Don't round, make it exact. I know on your graph it's going to look fine, but leave it exact. Don't round anything. Now I'm going to show you why we're going to run into some trouble here with 215. All right, if you're in Zoom Standard, it's because 215 is not actually going to show up on your graph. Do you know why? Because your y-axis goes up to 10, not 15. So, okay. But, I mean, clearly, we don't even care about what happens, I mean, down here. Who cares? So we're going to mess with our window a little bit. So for those of you who don't have as much practice with your graphing calculator, let's see. Oh, no, that made it worse. Okay, we'll try that and see. Go to your window, and we'll set our y max. Let's see. We know we need it to go up to 15. So let's send it up to 20. And if you want, you can even set your y min at 10. Sometimes with the window, I just like to play around with it and then see what it looks like. I'm going to have to adjust the x-axis too, clearly. And by the way, when you're looking at all of these, they're going to start to graph over themselves because it's so steep. Oh, there's your normal line. Clearly, it's perpendicular. But the tangent line looks like the same line. If you want to try to make this a little bit scaled out a little bit better, I mean, we went from 10 to 20, so that was only 10 units. If you'd like, maybe you could take x from 0 to 10. Honestly, you could try taking x from 0 to 5. See what that looks like. Why not? All right, so there's your graph, f of x, your function. This red line, I know doesn't look red to you, is your tangent, and there's your normal line. So your normal line should look like it's crossing perpendicular. It's kind of hard to tell in this case, but you should be able to eyeball it. The fact that these two lines graphed over each other, that's a good sign. That means that it looks like they're tangent. The problem is that this graph, being a cubic function, is just so steep that it's kind of hard to see that curve unless we really, I mean, we could mess with x a little bit more if you wanted to. I don't know, go from 1 to 4 and just keep kind of narrowing it in, seeing what happens. But we're probably still going to have a hard time getting a really good picture. It looks a little better. I don't know. I almost want to go to 3. I don't know if it's going to make a difference. Oh, well. There's your function. There's your tangent line. And here's your normal line. I know it doesn't look exactly perpendicular because remember, we're kind of scaled a little bit funny. The way that our screen is, it's not like this 1-to-1 ratio, but that's okay. You get the gist. Yeah. So that's kind of what you're seeing there. On WebAssign, it's going to ask you to graph all three, but it's going to be a multiple choice question. So you're going to have to pick the graph that matches the right one. But if you can't see the graph in your graphing calculator, then you're going to have to know how to manipulate the window a little bit in order to get that full picture. So make sure that you understand that you can go to your window. I mean, I would always start out in Zoom 6, Zoom Standard, and then kind of see what's going on. You know the points at 215. You know y only goes up to 10, so clearly you're going to have to raise that y maximum, if nothing else. I mean, let's say you weren't even sure what to do with your y's, and you were like, yeah, I don't know, let's just take it up to 20 and leave everything else the same. Well, if you did that, you would get a decent idea of what was going on. You'd be able to see the tangent line. Come on, tangent line. There it is. And the normal line. You might even feel like this looks better, honestly, just because at least you get a fuller picture in this case. Up to you. Okay. I'm not really worried about whether or not we can graph these things. I'm more focused on being able to use these limits and simplify them algebraically. So let's do one more of these. Okay. Sorry, I'm messing up my notes here all over the place. Let's do a rational function. I think it'd be good for us. We get to use some of these pre-calc review techniques too, which is always a plus. So your function is f of x is 2 over x plus 4. And we're looking at this at the point 1, 2/5. And remember that this is your c f of c. Okay, first we need f prime of c, which in our case is f prime of 1. So we're going to take the limit as x approaches c of f of x minus f of c divided by x minus c. Get used to writing that. We're going to use this limit a lot, and the more you write it, the more you're going to have it memorized, and the less you're going to have to worry about looking it up every time. So this is the limit as x approaches 1 of f of x. Now x is just a general value of x, doesn't matter. You're going to pick whatever you want at some point, but c is the specific value that we have. So x is the value that we're varying, c is fixed. F of c I gave you as 2/5, and then we'll divide that by x minus 1. Oh, you know what I did? I don't have my, this is why I don't like using a pen. I wrote f of x, but I didn't actually write the function f of x. You know what? That's okay. I'll just write it again. I don't know why I did that. That was odd, very odd. Okay, so here's f of x, f of c, and then in the denominator we have x minus c. Okay, now, but this is a complex fraction. And remember I showed you last week, I guess it was last week because I didn't know you the week before that. I showed you how to simplify complex fractions. So I'm going to pull this out of the limit so we can work on it. You're going to find that that happens a lot. No big deal. Okay. Now, when you're thinking about this complex fraction, the denominator doesn't actually have a fraction in it. If you want, you can write it over 1. You don't have to. If you find that to be easier, do it. We're going to multiply each term by the LCD. In order to do so, we need to note what the LCD actually is. So remember, the LCD is the product of all unique denominators, the greatest number of times they appear in any one denominator. So you have a 5, and you have an x plus 4, and you have a 1. So you have an x plus 4 once, you have a 5 once, you have a 1. Who cares about the 1? Your LCD is 5 times x plus 4. We're going to multiply each term by your LCD. In order to do that, I like to do this in a different color. Let's see if it shows up. I don't know. 5 times x plus 4, 5 times x plus 4, 5 times x plus 4. Every term gets multiplied by the LCD. Now, if you've done this correctly, you'll get your denominators to cancel out so that you no longer have a complex fraction. So in this first term in the numerator, the x plus 4s will cancel. In the second term in the numerator, the 5s will cancel. In the denominator, we don't have anything canceling at this point. So 5 times 2 gives us 10, minus, we still have a 2 times x plus 4, quantity, x plus 4. Don't forget your parentheses. And in the denominator, we have 5 times x minus 1 times x plus 4. Now, don't do anything crazy yet. Don't do anything crazy ever. But what I mean by don't do anything crazy is don't cancel out the x plus 4s. No. You have 2 terms in the numerator right now. You don't have an x plus 4 in this term. So you have to simplify it before you do anything else. Simplify this. 10 minus 2x minus 8. Don't forget to distribute that minus sign so that you have a minus 8. And 10 minus 8 is 2. So you'll have 2x minus 2, oh, negative 2x plus 2 divided by 5 times x minus 1 times x plus 4. And then in the numerator here, factor out your negative 2. And when you do that, 2 divided by negative 2 is negative 1. Make sure that when you distribute, you get back what you started with, negative 2x plus 2. The reason we're doing this is because we want these to cancel. Now they have canceled. And we can take the limit now of this simpler expression. Distribute if you'd like. Don't worry about it if you wouldn't like. Put your limit back together. We're going to take the limit as x approaches 1 of negative 2. You can put the negative 2 in front if you'd like. I'm just going to leave it for now. Over 5 times x plus 4. One plus 4. 5 times 5 is 25, and you get negative 2/25. And this is f prime of c, which is f prime of 1. That's the slope when x equals 1. And we need to find the tangent line and the normal line. And this is just algebra. Once you find the limit, you're just looking at y minus f of c equals f prime of c times x minus c. Y minus 2/5 equals negative 2/25 x plus 2/25. And then plus 2/25 plus 2/5 is 5. This plus 10, so that's what, 10, 12/25. 2 and 10 gives us 12. Okay, so this is the equation for your tangent line. Now, to find the equation for the normal line, almost the same exact thing, but this time you're going to take y minus 2/5 and set it equal to, and then take the opposite reciprocal of your slope. So it's already negative, so make it positive and invert your fraction. So instead of negative 2/25, you're writing 25/2 and then x minus 1. And then simplify. Y minus 2/5 is 25 halves x minus 25 halves, and y equals 25 halves x. And put this in your calculator if you would like. So this would be negative 25 halves plus 2/5, and then math button right here, enter, enter, and you get negative 121/10. So minus 121/10. This is the equation for your normal line. I'm not going to worry about graphing these. I think that you guys can graph those in your graphing calculators and generate a picture just fine. I'm not too worried about that. Okay, so we talked about tangent lines. We talked kind of in a more abstract sense about the slope. So now I'm going to ask you to do something very similar, except I'm going to change the wording a little bit. And partly I do this because it allows me to give you, it allows me an opportunity to give you different types of functions. So I do want to talk about different kinds of functions. All right, so let's formalize this idea then. Definition: derivative of a function at a number. So talking about finding the slope at a specific value of x. If y equals f of x is a function and c is in the domain of f, then the derivative of f at c that's what we're defining here. Remember, this is f prime of c is the number f prime of c is equal to the limit as x approaches c of f of x minus f of c divided by x minus c. And we've used this a couple times already today. Put a cloud around it, or whatever you need to do to make it stand out to you. I would like to also state that a derivative is a slope. Right now, we're going to talk about finding a derivative at a number. That means focusing on one particular x value on our graph and saying, okay, like let's find the slope at this particular value. Into 2, which I'm going to start in a couple of minutes, we're going to find a general equation, or I'm sorry, a general expression to find the slope at any given value on the curve. But right now, we're just focusing on looking at what is the slope at this point. And to do that, we're going to use this formula. I also wanted to state a derivative is a slope. I'm going to keep saying it over and over again. It's not some weird abstract concept. A derivative is a slope. That's all it is. Example 2. Find the derivative at a point. So if you're wondering, like, didn't we just do this? Yes, you did. But before I asked you to find the equation of the tangent line, this is almost easier because I'm not asking you to find an equation of the tangent line. I'm just asking you for the value of f prime of c. Okay. F of x equals the square root of x, and we're going to figure out what the derivative is at 9. Now, the other slight difference between example 2 and example 1 is that in example 1, I gave you the point CF of C. But that's not really a big deal because in this point, I'm asking you to find the slope at 9. That means we're letting C equal 9. So to find f of C, we're just looking for f of 9. And we're just going to evaluate this function. So f of 9 is the square root of 9, which is 3. So our point CF of C is 9, 3. So if I were you, that would probably be the first thing that I would do. Just find the corresponding y value if you are not given that value. I should keep this here. There we go. Okay, and then what we have to do then is find f prime at 9, which is equal to the limit as x approaches 9 of f of x, which is the square root of x, minus f of c, which we just found to be 3, divided by x minus c, which is x minus 9. Two ways of doing this. If you want, you can think about x minus 9 as being the difference of two squares, where x is the square of the square root of x. Or if I were you, I would suggest using the conjugate because it's something that we used in this class a lot anyway. Notice that if you tried to evaluate the limit straight from here, you'd have the square root of 9, which is 3, minus 3, which is 0, divided by 0. So it'd be an indeterminate form. So let's focus on figuring out the value of the limit, since we do get an indeterminate form. And we'll do that by finding the conjugate. So we'll multiply by the square root of x plus 3 divided by the square root of x plus 3. And we will get x. The inside and outside terms cancel because it's a conjugate. Don't forget to leave the denominator factored. And now you can see why. The x minus 9s cancel. And that leaves you with 1 over the square root of x plus 3. Now you can go back to your limit and put this expression back into that limit. So now we're looking for the limit as x approaches 9 of 1 over the square root of x plus 3. Which is 1 over 6. I think you can check this in your calculator. I hate showing these calculator things because I don't want you to become dependent on it, but I haven't seen students become dependent on this, so we might as well show it. Go ahead and graph the square root of x. And it's just a nice way to check your work if you can, right? Okay. Graph the square root of x. I'm in a standard zoom, even though I know the domain's only values of x that are greater than or equal to 0. I believe you can go to calculate, which is second trace. And you can find it. We're going to talk about this notation next week, but the dy dx denotes a derivative. That's number 6. And you can input a value of x. So we're looking for the derivative at 9. All you have to do is just type 9, and it will show up in the box down here for x. And then hit enter. And then it will give you have to hit enter again. Oh, never mind. It's right here. I'm not clearly even reading my screen. It gives you the value of the derivative at x equals 9, y equals 3. The value is 0.16 repeating. Well, that's 1/6. So, I mean, yes, technically you would have to know that decimal approximation, but what 0.16 repeating is 1/6. So that's just a way of kind of checking the derivative at the point using your calculator. We're not going to be doing a whole ton of derivatives at a point outside of this section, but you have that at your disposal to check. Okay. Let's do one more of these using a rational function, and then we'll talk about maybe in 2.2 finding more general derivatives. So this will be 2 plus 3x divided by 2 plus x, and we're going to find the derivative at 1. Now, remember what I said. I think the best thing to do would be to start just making sure we know what f of c is. F of 1 is 2 plus 3 divided by 2 plus 1, which is 5/3. So we're looking for the derivative at 1 5/3. That's your c, f of c. I might possibly run out of space here. We're going to find out. We're going to take the limit as x approaches c, which is 1, of f of x minus f of c, we just found was 5/3, divided by, well, where is it? Oh, yes, x minus c. X minus c, which is x minus 1. And again, we have a complex fraction. This is why I spent time talking about those last week. You're going to see them more often than you might imagine. Again, if this is bothering you, make your denominator a fraction also by putting a 1 underneath it. Sometimes it helps students to just see every quantity as a fraction. We're going to work outside of this limit, but first let's note that the LCD is going to be 3 times the quantity 2 plus x. Every denominator you see, the greatest number of times it appears in any one denominator. So let's go ahead and simplify our complex fraction by multiplying through. I'm going to rewrite mine here. All right, so we're going to multiply each term by our LCD. If you would like to put parentheses around your binomials, if you find that helpful, you don't want to forget about the parentheses, I would strongly suggest that as a good idea. Cancel what you can. Remember, you should be able to get rid of all of your denominators. And then we'll simplify. So in the numerator, in the first term, we have 3 times 2 plus 3x. In the second term, we have, let's see, 5 times 2 plus x. We'll distribute to simplify it in a minute. And we also have 3 times x minus 1 times 2 plus x. Remember, do not cancel out the 2 plus x. You can't do that because you don't have 1 in every single term. You're going to have to distribute and simplify. Don't forget to distribute that negative sign. If I were you, I would leave your denominator factored. My guess is that you're going to get something that's going to end up canceling out once you simplify your numerator. 9x minus 5x is 4x. 6 minus 10 is -4. And there's where you're starting to see that things are working out nicely. I'm going to switch 2 plus x to x plus 2. Just because I can, factor out that 4. And now you can see where you're going to be able to cancel out those x minus 1s. And that leaves you with 4 divided by 3 times x plus 2. And again, it's up to you if you decide you want to multiply that in. It doesn't matter because we're just going to be taking the limit as x approaches 1 of this quantity, which is going to be 4 divided by 3 times 3, which is 4/9. Okay. So that was 2.1. That was 2.1. Let's talk about 2.2. So we've laid the groundwork. Now we can get into talking about more general functions here in 2.2. So we're going to be using these same concepts. This is the derivative as a function. So being able to actually talk about the derivative instead of being f prime of c, being f prime of x, and just talking about what the slope would have to be at any given value of x. I'm going to give you an alternative form of the derivative. And this is what we're going to be using a little bit more in this lesson, although it is interchangeable. F prime of c is equal to the limit as h approaches 0 of f of c plus h minus f of c divided by h. And if you're thinking like, wow, this looks really familiar, where have I seen this before? It's the difference quotient, just with a c instead of an x. And we talked about the difference quotient earlier in the week, talking about finding those limits. I gave you an example in class. You had maybe two of them on your homework. But we're going to use that here to find the derivative. Yeah. And by the way, this is not some crazy weird thing. We're just kind of switching this out a little bit where h is just representing x minus c. So taking that difference. So instead of x approaching c, we're just talking about that difference between x and c approaching 0. So what's happening as the difference between x and c gets smaller and smaller and smaller and smaller and eventually heads over to 0. That's the only thing this form is doing. It's just swapping that out with h and sending it to 0. Okay, example 1. We're going to use the alternative form of the derivative to find the derivative of a function at any number c. So we're going to use the alt form of f prime of c to find the derivative of f of x equals x squared plus 9x at any number c. Okay. Ready? Ready? Okay. In this case, first of all, we need to find f of c plus h, and then we're going to work on this difference quotient. So same as what we were working on last week every time we did these. I only did one in class, but you did 2 or 3 of them on your homework. All right, f of c plus h. Everywhere you see x, swap it out with c plus h. So we're going to have c plus h squared, which means c plus h times c plus h, plus 9 times x means 9 times c plus h. So just using the same function and substituting c plus h everywhere you see x. And then we're going to simplify that. So c squared plus 2ch plus h squared plus 9c plus 9h. Now we're going to take that quantity, subtract f of c, and divide by h. So let's see. This is terrible because it's like 1 in the morning and I'm doing this and I'm getting these messages from my sister that her baby's just not sleeping and I feel terrible for her. And now I'm like all distracted, but they just pop up and I feel really bad for her. Because I've been there myself. I don't know if any of you have kids. Oh, When your kid won't sleep, it's like a nightmare, like a total nightmare. All right, anyway. All right, so we're going to look for f of c plus h minus f of c divided by h. So c squared plus 2ch plus h squared plus 9c plus 9h minus f of c, which is our function value at c. So not f of x, but f of c. And remember that you're going to have to take, this is two terms, use parentheses, because that whole thing gets subtracted off, and you want to make sure that that negative sign gets distributed. Okay. And then divide that by h, and then we'll simplify again. If you want to put your limit back on, fine. But you can wait until you're done. It's not a big deal. Wait until you're ready to actually apply the limit. All right, so simplify. Now, remember what I said. If you've done this correctly, I was saying this last week, then you're going to get both of these f of c terms that you're subtracting off to cancel out. They'll be additive inverses. So like c squared and negative c squared, gone. 9c, negative 9c, done. And that leaves you with 2ch plus h squared plus 9h divided by h. And in this case, we have an h in every single term. You can go ahead and cancel it out. If you feel more comfortable factoring and then canceling, then do that. Factor an h out of the numerator. And then what you'll have left is 2c plus h plus 9. Okay, and now we have f of c plus h minus f of c divided by h. That was what we just found. So go ahead and take your limit as h approaches 0 of 2c plus h plus 9. Now remember, the only quantity that's going to 0 is the h. Everything else you're treating like a constant. That is the derivative at any number c. Now, we just did this for c. What we're going to be focusing on going forward is just swapping out c with x. So I'm going to give you the definition for the derivative function. And we're going to be using this process to find derivatives. And we're going to talk about this value being some function of x. You know what, though, before I get rid of this, I want to plant the seeds for you here. This is going to be, we already said f prime of c. This is just the derivative at any number c. What this means, though, is I can let c be any number I want, and this formula is going to tell me the slope at that number. So let's say I'm talking about this graph, and I want to know, well, what's the slope at 1? Well, if I have a formula for the slope, I can talk about what's actually happening at 1 by letting c be 1. Well, if c is 1, I know f prime of c is 11. Now, that should make sense because this is a pretty steep quadratic graph. So, so that's kind of what we're going to be heading towards at this point. And you know, if you have this written as some function of c, you can figure out the slope at any point c that you want. So instead of like in the last section where I specifically stated find f prime at this value, now you're going to be giving me this derivative as some function of c or some function of x so that you can figure this out for any value of x that you would like. So without further ado, let's keep on keeping on. The derivative of a function, the derivative function f prime of a function f, I should say that. The derivative function f prime. Something weird is happening. Should I? Okay. Never mind. the derivative function f prime of a function f. My worst nightmare is that I'm going to be recording this lesson. It's going to be like 2 hours long. And for some reason, like either I wasn't sharing or like it never actually recorded. I'm always paranoid. I'm constantly checking, like, is it recording? Like, I don't want to have to redo this whole thing. It appears to be recording. The derivative function f prime of a function f is. Now, here's where that alternative form of the derivative comes back around. F prime of x is the limit as h approaches 0 of your difference quotient, f of x plus h minus f of x divided by h, provided the limit exists. Okay, so if the limit exists, then the derivative function f prime of our function f is f prime of x equals the limit of this difference quotient as h approaches 0. And this is going to give us a general function f prime of x that will allow us to plug in any x we'd like to find the derivative at any point we're being asked to find it for. Now, if f has a derivative, then f is said to be differentiable. So if f has a derivative, then f is said to be differentiable. Differentiable. We're going to be using that term a lot, especially as we head into chapter 4 and chapter 5. We're going to be given lots of theorems that say, you know, if your function is continuous on this interval and differentiable on that interval, what it means to be differentiable is that the derivative exists. So when we talk about being differentiable on an interval, we just need to verify that for every point in that interval, the derivative exists. So later on in this section, we'll talk about finding values for which a derivative might not exist on a given function. But for now, we're just going to stick with this definition and work with this to find f prime of x for another function, another radical function, because I think these radical functions are really good to work with. Example 2, find f prime of x and its domain. Find f prime of x and its domain. It's important that we know the domain of f prime because we need to know where this function is differentiable. F of x is twice the square root of x plus 1. So I'm giving you a function f of x. And what we're going to do is we're going to find f prime of x. And f prime of x is giving us a general formula for the derivative that we can use to find the derivative at any given point we'd like. In order to do that, I need to first work on finding the limit of this difference quotient. So recall that we have this limit as h approaches 0 of f of x plus h minus f of x divided by h. And as you might be thinking at this point, we have a limit that's going on. It's approaching, h is approaching 0. We have a radical function. This might involve the conjugate. And if you're thinking conjugate, good job. You're right to be thinking conjugate, but we're not quite there yet. We're going to have to get there. But if you're sort of thinking ahead at what we might be heading towards, you're on the right track. Good job. All right. F of x plus h minus f of x divided by h. Now this one's not quite so complicated to come up with f of x plus h because you're not squaring it and adding it to more terms. So let's go ahead and just pop this all in together. F of x plus h is just our f of x, and everywhere you see x, swap it out with x plus h. And then minus f of x divided by h. Gosh, you can tell how much I like this stuff because it's 1 in the morning and I'm just like really pepped right now. It helps that I did a little yoga after our evening session, put the kids to bed, did a little yoga. I'm totally primed for derivatives. Okay. Now, by the way, I wanted to mention, if you weren't sure, like, why would I need the conjugate? If you tried to apply the limit right here as h approaches 0, well, notice right off the bat the denominator would be 0. But look at what else would happen. If h was 0, then you'd have twice the square root of x plus 1 minus twice the square root of x plus 1. You'd get 0 divided by 0, which is an indeterminate form. I know it's unfortunate, but it's, you know, part of our lives at this point. I guess you could technically factor the 2 out if you want. I'd be a little weary of that, though, because I'd be worried that I would forget about it, and I don't want to do that. So let's go ahead and keep the 2 on here, and we'll multiply by the conjugate. We'll just switch the sign between the terms. Just like that. Now we'll multiply. If you prefer to have parentheses around it and you feel like you can FOIL more easily, that's fine. Put parentheses around it. I'll leave that up to you. You do what you want to do with that. The first terms, 2 times 2 gives you 4. The square root multiplied by itself just gives you x plus h plus 1. The outside and inside terms are going to cancel out. That's the whole point of the conjugate. And then we're going to have minus 4 times, and then the square root of x plus 1 multiplied by itself is just x plus 1. In the denominator, remember we usually leave this factored. I still would suggest you do that in case you get to a point where you see that you shouldn't. I would do so. Just leave it factored. Okay. So here's where we are right now. We're probably going to get some stuff to cancel out here. So let's go ahead and simplify the numerator. 4x plus 4h plus 4 minus 4x minus 4. And you can see now that if you really want to, it's driving you crazy now. Get rid of it. And now we can see it's a really good thing that we left the denominator factored, because now we can see that we have an h that will cancel between the numerator and denominator. I'm going to do that in the next step. It's up to you if you want to cancel that now. I just don't want it to look confusing between the additive inverses and the common factors. So I'm going to write the numerator as 4h, and then the denominator. I know it's driving you crazy. You're just like, why is she rewriting this stuff over and over? Because I'm the teacher. I got to show every step. I don't want there to be any questions. I can't ask you right now, does anyone have questions? Because you can't give me your questions in this format. So got to write everything so that there's no confusion. Cancel out your common factors of h. Now at this point, you might want to pop your limit back on. Otherwise, you're going to have to rewrite this whole thing again, and nobody wants to do that. Might as well leave the 4 in the numerator. Up to you. But you shouldn't have to worry at this point about getting in a determinate form because your numerator is a constant. Send h off to 0, and that leaves you with 4 divided by twice x plus 1 plus twice the square root of x plus 1. Sorry, I meant to say square root x plus 1, not just x plus 1. But the h in this case went to 0. X plus 0 plus 1 is just x plus 1. Now we're going to simplify this. We're not done yet. So twice a quantity plus 2 more of them is 4 of them. It's like saying 2x plus 2x is 4x. You have this x plus 1 under the radical twice. So, or I should say 2 sets of 2. And then you end up with 1 divided by the square root of x plus 1, and this is f prime of x. Okay. So we started out at the beginning, we had our original function. We found this difference quotient right here, f of x plus h minus f of x divided by h. We had an indeterminate form when we tried to apply the limit. So we multiplied by the conjugate, went through a bunch of work simplifying, and we ended up down here at our derivative. I asked you also, though, not just to find f prime of x, but also to find its domain. So let's do that, because we need to know where this function is differentiable, which means where we can possibly take the derivative. Now, we talked on the first day of class about finding domains of radical functions and rational functions, and I even gave you an example where you had a rational function with a radical in the denominator. First of all, we need to verify that x plus 1 is positive. And in this case, I don't want to say that it can also be equal to 0. Normally with the radical, we just want the radicand to be greater than or equal to 0. But because this is in the denominator, I don't want to divide by 0. I want to force this quantity to only be positive. And that leaves me with x is greater than -1. So that means for a value of x that's greater than -1, f is differentiable. So I could say f is differentiable on this interval. F is differentiable on this interval. That means I can take the derivative of our original function f of x, which was twice the square root of x plus 1, on this interval. So I can pick any value in this interval, and I can find the slope of f using f prime of x. Okay, so that's what that means. I know, and this is all really new to some of you, and that's okay. All right, so we looked at a variation of this where we looked at f of c and found f prime of c. We looked at one where we found f prime of x. Okay, let's just do one more. I feel like we should do one more of these because we did a couple radicals, but we didn't actually do a cubic function. I want you guys to feel gypped. Never want that. Okay. I want you to have the full derivative experience. All right, example 3, graph. You know, I'm not going to say graph. I'm not going to worry about that. I'm just going to say find f prime of x using the alt form of f prime of x. Or I should say the alt form of the derivative. Okay, f of x we're going to let be equal to negative x cubed minus 8. And this is really just an exercise in algebra at this point. So I'm going to go through this one slightly more quickly. Okay. So remember, I'm looking for the limit as h approaches 0 of f of x plus h minus f of x divided by h. All right, here we go. Ready? F of x plus h is going to be negative x plus h cubed. Don't forget, when you cube a quantity, you have to multiply it out 3 times. And then minus 8. Okay. My suggestion would be to FOIL the second 2 factors and then multiply in the first binomial. So you have x squared plus 2xh plus h squared. Now you can go ahead and multiply in. If I were you, I'd multiply in the binomial and then multiply in the negative. So start with just multiplying every term by x, then multiply every term by h. So like distributing a binomial into a trinomial. Okay. X, I'm putting parentheses here because I don't want to forget that this negative gets multiplied in. So don't forget your parentheses. X cubed plus 2hx squared plus h squared x. Now we'll multiply in the h. So we'll have plus hx squared plus 2h squared x plus h cubed. Now, if you remember Pascal's triangle, you can do this more quickly. I rarely have students who remember it. Half the time I don't remember it. For a cube, I would. Okay. X cubed, you have hx squared and hx squared. You should have 3 of them. Remember, if you remember your Pascal's triangle, you guys remember 1, 3, 3, 1. No? Algebra 2? Oh, well. Some of you will remember. Usually have at least a couple who do. So we had hx squared. We had 3 of those, and then we have 3 h squared x's. And then h cubed, and then minus 8. And then multiply in that negative. Negative x cubed minus 3hx squared. Whoop. Minus, oh, I hate pens. I only don't use pencil at this table because of the way the light kind of glares. It's really hard to see the pencil. I strongly recommend that everybody use pencil all the time. Now, there's nothing you can do to simplify this, but this is just f of x plus h. We're going to take that, we're going to subtract off f of x and divide by h. So here's where we're going now. If you're just like, why are we writing it again? You can just kind of build it off what we already have. I don't know. Clearly, I'm just a glutton for punishment here with this writing. My hand is really starting to ache. I'm going to subtract off f of x. And, you know, I might have almost said, just distribute the negative and don't bother with your parentheses. But because both signs are already negative on here, I feel like it's going to get lost. So I'm going to do one more step as I complain about my hand being sore. All right, so we have f of x plus h minus f of x. And we'll simplify. So negative x cubed minus 3hx squared minus 3h squared x minus h cubed minus 8 plus x cubed plus 8 divided by h. Now, again, if you've done this correctly, you're going to get these terms at the end to cancel out. And then most of the time you'll find, especially with these polynomial functions, that you're going to get a factor of h to cancel out so that you can cancel out that denominator. So I'm going to take out a factor of h. If you would like, if this negative is bothering you, because it really is bothering me, take out a negative h. It doesn't matter, but it's bugging me, so I'm going to take out a negative h. That might even throw you more because your signs could get screwy. So if you don't feel comfortable, just leave it in. And then plus h squared divided by h. All right, so that was one h, bye-bye, another h, another h. And then I took out the negative, so all the signs swapped. And this is just going to be negative 3x squared plus 3hx plus h squared. And the h's here cancel. Now we're going to take the limit as h approaches 0 of negative 3x squared plus 3hx plus h squared, which is just negative 3x squared. And then if h is going to 0, both of these terms go to 0. And then you just get negative 3x squared is f prime of x. My beverage is gone. Disheartening. All right. Okay, so that's the derivative which I asked you to find. What I want to do now, actually, I only really have one more example here. But before I do that, I want to talk about how to relate a graph and its derivative, and how they're similar, how they're related, really. So what I want to do is graph f of x is x cubed plus 2x squared minus 5x plus 4. Now, I'm going to give you the derivative in this case. I don't remember where I got this function, if it was from this book or from another one. I can't remember. Somewhere. I'm giving you the function. Here's the derivative. We're going to graph these on the same set of axes. And I want to talk briefly just about how these two graphs are related, even though they're going to seem very different. You would find some surprising relationships between the two. X cubed plus 2x squared minus 5x plus 4. And then we'll graph the derivative as y sub 2. And this, by the way, these are random. This is a random function not related to example 3. I don't want you to be like, where the heck did she come up with this? Okay. I'm going to go back to Zoom 6. Okay. Now, there's f of x. There's its derivative. Notice that f was cubic and its derivative is a quadratic function. It's parabolic. But you can't see what's happening up here. So you're going to want to switch your window out. I'm just going to raise it up a little bit. And if you're not sure how far, just guess and then see if you need to raise it farther. But I want to see more of the picture. So I'm going to switch my y max up to 15. There we go. There's our original cubic function. And here comes our derivative, which is quadratic. Now, we haven't done a ton of these, but you'll notice how anytime you take the derivative of a polynomial function, the derivative of the polynomial is 1 degree less than the original. So you're kind of seeing that illustrated here with the cubic and the quadratic function. All right. Here's what I want you to notice, and it's subtle, but important. And I'm going to zoom in a little bit, actually, on this thing so that everybody can see this. Zoom. It's beautiful. Okay. Terrific. What I want you to see here is that your original function increases up until it hits this point. Now, we kind of talked earlier, and I'm going to mention it again, even though there wasn't a ton of emphasis. I mentioned it, but I want to keep sort of mentioning this because I feel like I'm just like planting these seeds right now. You get to the top of this hill on your function, and if you're thinking about this as it relates to tangent lines, you would have a tangent line at the top of the hill that's horizontal. Okay, fine. And then after that horizontal tangent line would hit, you see now that on your cubic function, it starts to go down again. So notice how this relates to your derivative. I wish this showed up in colors for you. It's, for me, the cubic is blue and the derivative is red, but you know what? Nothing I can do about that. As your function is increasing, up until the point where it stops increasing, your derivative is positive. What I mean by positive is I mean the y values are positive. So all these y values lie above the x-axis. But as soon as your function hits this point where you would have this horizontal tangent line and then it starts to decrease. Well, while your function is decreasing, its derivative is negative. See, it's all below the x-axis. So at this point where you have this horizontal tangent line on your function, your derivative has an x-intercept. So your function decreases, decreases, decreases up until it gets to this point, which is this little dip here in the graph where you would have another horizontal tangent line. Well, look at what's happening to your derivative at that point. The derivative function has a situation where it stops being negative and it hits this x-intercept at that point. So it hits the x-intercept and then your function starts to increase again. And as soon as your function starts to increase again, your derivative becomes positive, meaning the y values are all going to lie above the x-axis. This is actually really cool and exciting. You might want, there are probably some really cool pictures in your book of similar graphs. There might be like 2 of them on the homework that'll kind of ask you, like, if this is the function, which one is the derivative? But that's what you're supposed to be getting out of this. When your original function is increasing, the derivative function is going to have only positive y values. When your original function stops increasing or decreasing, your derivative function is going to have an x-intercept. When your original function is decreasing, heading downwards, your derivative function is going to lie below the x-axis. And then as your original function starts to increase, your derivative becomes positive. Very cool. Very cool. All right. We'll take this back to my normal Zoom. My normal Zoom keeps changing. It's unclear. There's a large threshold. That's probably why. Okay. All right. Now, we've seen that. Let's talk. The last thing I want to talk about here is finding values where a function might not be differentiable. Let's do that. Okay. Suppose a function f is continuous on an open interval containing c. The function f has no derivative at c if the limit as x approaches c of f of x minus f of c divided by x minus c, taking you back to this original form of the derivative, does not exist. Now, if you're wondering, well, why did we use an alternative form and then come back to this original? When you're trying to show that a derivative is not differentiable at a point, you go back to this original. The original we usually discuss when we have a specific value of c in mind. In this case, we're going to be talking about values of c for which our function might not be differentiable. So if this limit does not exist, then the function is not differentiable at this point c, whatever point that might be. So let me give you some possible scenarios here. It could be that the one-sided limits exist, but are not equal. That's a scenario that you might encounter when you're trying to apply this definition of the derivative at a specific value c. It could be that you approach c from two different directions and the one-sided limits are not the same. If this is the case, then f has something called the corner at c f of c. Usually a corner is just like a sharp point on the graph. So that's one thing that you need to look out for is a sharp point on the graph. Look out for sharp points on the graph. If you have a sharp point on the graph, that's where you're going to check for issues with differentiability. And that's a case where you might have a situation where your one-sided limits do not exist. Another scenario would be that your one-sided limits are both negative infinity or positive infinity. If this is the case, then f has a vertical tangent line at c. I'm going to show you an example of this in a minute. And if you have a vertical tangent line, then we can't possibly be differentiable there because we can't possibly create some function of x there. Another scenario is that both one-sided limits are infinite, but one is positive infinity and one is negative infinity. One-sided limits are infinite. But one is negative infinity and the other is positive infinity. Then f has a vertical tangent line and a cusp at cf of c. I'm not going to be asking you on your test to tell me about corners and cusps. Mostly, I just want to be able to give you a function and have you figure out values of x that you think might cause issues with the differentiability, and then to use the definition of the derivative to prove to me that that limit does not exist. And I'm going to give you two examples now of how to do that. Example 4, find c such that f prime of c does not exist. So I'm going to give you two of these. One of my favorites is this piecewise function. So it's going to be f of x equals negative x minus 3 for any x less than or equal to negative 3, and x plus 3 for any value of x that's greater than negative 3. Okay. I suggest you graph it. I always like to graph piecewise functions. You know that. You know that about me. But I think it'll help you. You don't technically have to graph it in this case because you know where the issue is going to lie. I mean, these are linear equations. Where else might they have a problem with differentiability if not the boundary points? You already know that c equals negative 3 is going to be the issue. Well, let's graph it because it's good for us. X is greater than negative 3 follows x plus 3. So this is for x being greater than negative 3. I'm going to go ahead and graph this line, y equals x plus 3. In the case that x is greater than -3, I'm not filling in the circle here because I didn't say greater than or equal to. So when x equals -3, f of x is 0. When x equals -2, f of x is 1, so on and so forth. If x is less than or equal to -3, I'm going to follow this function. If you want, you could just draw the function and then dash it. Or you can just, use values of x that are less than or equal to -3. So if x is equal to -3, -3 is +3, -3 is 0. So you can go ahead and fill that circle in now. If x equals -4, -4 is +4, -3 is 1. So you can start to see you've got this slope of -1. The y-intercept is -3 if you were to actually take it down that way. And you have y equals -x minus 3. Okay, that's what the graph looks like. It's helpful to graph because you can see now that you have what appears to be a corner. Now, this might not be an issue for you, but we're going to check because anytime you have a sharp point on your graph, you're looking at a scenario where it's very possible that the function's not differentiable at that point. So let's verify this by looking at the one-sided limits. We're going to first look at the limit as x approaches, again, -3, because that's the only place where anything interesting is happening, from the left and from the right. So we'll start by looking at x approaches -3 from the left. And when we approach -3 from the left, we're looking at this function for values that are less than or equal to -3. So I'm going to go back to my definition, remind you of it since we haven't used it since 2.1 like an hour ago. F of x minus f of c divided by x minus c. So f of x, in our case, will be -x minus 3. F of c is f of -3, which we found to be 0. So we'll go ahead and subtract off 0. Divided by x minus c, which is x minus -3. And then we'll simplify. So this is the limit as x approaches -3 from the left of, in the numerator we actually have, if you want to factor that negative out, we have negative quantity x plus 3. And in the denominator, we just have x plus 3. Well, cancel out the x plus 3's, and that shows you that we have the limit as x approaches -3 from the left of -1. So you're technically canceling those out. The limit of a constant is the constant itself. The left-sided limit is -1. All right, so let's focus now on the right-sided limit. We're going to approach -3 now from the right. So again, we're looking at f of x. Well, if we approach from the right, we're on x plus 3 minus, and then we're looking at f of c. Well, f of -3 actually still corresponds to this point here at 0. You can use your function to determine that. And then we'll subtract off x minus, and then c is -3. And cancel out the x plus 3's, and you get 1. The limit of a constant is the constant itself. Your left-hand limit is -1. Your right-hand limit is 1. So your slope as you approach from the left is always going to be -1. Makes sense, right? Your slope as you approach from the right is always going to be +1. And you can't reconcile that between these two. At this sharp point, we actually have a case where the left and right limits do not agree. So in that case, yes, we have a corner, and we would say that this limit does not exist. Therefore, f is not differentiable. F is not differentiable at x equals -3. That's our big conclusion here. And I'll do one more of these. And again, anytime you see a sharp point on a graph, and a lot of times you're going to see sharp points on these piecewise functions or absolute value graphs, you're going to have a situation where the function's not going to be differentiable at the sharp point. Such is life. Example B. This one's maybe not quite as intuitive. It's not as obvious right away that you would have an issue. This is f of x equals x to the 1/5. Now, you're looking at this function and you're like, okay, fine, like where might I possibly have an issue with differentiability? Well, if you're not sure, graph it. You have x to the 1/5 power. Graph it. I'm still in a weird zoom, but it's not that weird, I guess. Okay. Now, nothing interesting is happening over here. Nothing interesting is happening over here. The only interesting thing that's happening on this graph happens in the middle. If there's nowhere else you can think of to look at, look at x equals 0. Okay. We're going to go back to our definition here for the derivative. We're going to take the limit as x approaches c, which in our case will be x approaches 0. F of x minus f of c, well, f of 0 is 0 to the 1/5, which is 0. So f of x minus f of c divided by x minus c. And this leaves you with x to the 1/5 divided by x. And we talked a lot about this in class when we were looking at section 1.5. Use your exponent rules. Subtract the denominator's exponent from the numerator's exponent. Keep your base. And again, I know I'm writing so much. This is 1 over x to the 4/5. Remember that when you have a negative exponent, you can make it a positive exponent by switching its position in the fraction from numerator to denominator or vice versa. Now, this is a problem because as x approaches 0, we can't divide by 0. The limit does not exist. Doesn't matter what the limit is. If it's positive, negative, infinity, doesn't matter. All that matters to us is that the limit does not exist. And if the limit does not exist, then the derivative does not exist at that point. So we would say that f is not differentiable at x equals 0. F actually has a vertical tangent line at that point. And I mean, I could pop my graph back up here. We would have to zoom in very closely. All right, so let's zoom standard. And you would have a hard time seeing that and kind of get an idea of what's going on. But maybe zoom 2 and enter. You get a closer view. And you can see how rapidly this graph is increasing as it's sitting at the origin. And actually, interestingly enough, my calculator actually splits the pixels here. You can't even see that these are connected for the segments of this curve. And they do that because it's vertical, and your calculator cannot bring itself to graph a function with a vertical line in it. So it kind of knows like, oh, can't do this. And it doesn't even try to connect those. If your graph has a vertical tangent line at a point, then it's not going to be differentiable at that point. I'm going to give you a theorem, and then I'm going to give you a corollary, and then I'm going to be done. And you can go on and enjoy the rest of your weekend. Hopefully you're watching this at the beginning of the weekend and not Monday afternoon. I'm trying to give you like mad eyes. Don't watch this on Monday afternoon. Come on. I mean, it's better than not watching it at all. You know, you guys are so good. I think it's Friday night and you're just like, man, I wanted to go out with my friends, but I think I'm going to do calculus instead because it's so fun. And because I don't want to save this until Monday afternoon. Theorem, if f has a derivative at a number c, then f is continuous at x equals c. So if the derivative exists at that number, then it is a given that the function's continuous at that number. Corollary, if f is discontinuous at c, then f has no derivative at c. So we would say that the condition of differentiability is stronger than the condition of continuity. I mean, think about what happened back there with that absolute value graph. Well, it looks like an absolute value graph. It was a piecewise function. But, I mean, think about this. Trying not to run out of space. For this graph, your function was continuous. We could graph the whole thing without ever having lifted our pencils. This function is continuous at -3, but it's not differentiable at -3. So continuity is easier to attain than differentiability. So it could be the case that your function is continuous at a point, but it might not be differentiable at a point. However, the converse is going to be true. If your function's derivative at a point, then that automatically guarantees it's continuous at that point also. And then thinking about that in another way, if your function's not even continuous at a point, then there's no way the derivative is going to exist at the point. The derivative is a stronger condition to meet. Okay. That's all I have for you. That was 2-1, 2-2. I think it was like 2 hours. It's totally fine. You guys are fine. Everybody's fine. It's all good. On Monday, I'm going to talk about derivative rules in 2.3. Maybe start a little 2.4, which I believe is product and quotient rules. And chapter 2 is going to fly. It's going to fly by you. Yeah, 2.4 is product and quotient rules. 2.5, I believe, is, 2.5 is trig functions. And then you have another test. It's on the schedule. It might even be next week, Thursday. I would have to verify on the schedule. Chapter 2 is, I stated this in class, it is going to be your easiest chapter. The derivative rules that we're going to be talking about in chapter 2 are easier than the ones in chapter 3. The ones in chapter 3 aren't crazy, but chapter 2 is really where you should be catching up and making up for some lost points that maybe you acquired in chapter 1, or maybe I should say did not acquire, or maybe that you anticipate maybe things might not go as well later on. Who knows? It's a short summer. Hopefully everything will go swimmingly. Students always do better in the summer, always. It's counterintuitive, but they do. So I think everyone will be fine. But next week, 2-3, 2-4, 2-5. And then your chapter 2 test will just be here in no time. So 2-1, 2-2, I'm going to put up some homework. And I want you guys to enjoy the rest of your weekend. You're doing great. Keep up the good work. That's all. If you have questions, send me an email. We will discuss. And stop in for the office hour on Monday at 5:30. Hopefully my children won't be making a ruckus, but they probably will be. But who cares? It'll be fine. Have a wonderful weekend, you guys.